Hello, Smarthome community. Many of you know already how MQTT works, but why, and more importantly, how should we use MQTT in our home automation system in the right and most suitable way? Where and how should we use it so that we get the maximum benefit from it? Using it in the right way, MQTT can help all of you to make your home automation system much simpler and more compatible than you probably think. Welcome to my first video here on YouTube. In order to decide which tool we should use for which function or task, we must not only learn the functions of that tool, but more importantly need to understand its interfaces. I mean tools like Home Assistant, Node-RED, I/O Broker and so on. Which technology should we use for the connectivity, like Wi-Fi or Zigbee? How to integrate any peripheral components into the system and how to distribute the signals and commands. How to set up the main control logic, where should it run and how should it communicate with the components. Since there is no universal answer to a question that generates a lot of individual opinion and experience for each of the available tools, nobody can recommend the best solution for every user in the world. All beginners are left with this dilemma. They must make their experience and learn it the hard way. They must change their concepts and solutions rather often before they can dive deeper into the automation optimization. Fortunately, there is a shortcut by using MQTT right from the beginning, because MQTT offers exactly that flexibility that everyone needs in every phase of a project for adding or modifying functions, connecting or replacing any type of hardware components. That is why I show here what advantages MQTT offers for the Smarthome Control and how we can use it for our home automation system. I explain the basic principles and show simple examples out of practice. Furthermore, I show some rules and processes that we should follow in order to get safe, stable and redundant Smarthome Control systems, and for which MQTT plays an important role. The MQTT broker is for me the most important player in the system, but only for the distribution of signals and messages. It is a very powerful and efficient communication tool for signals and commands, but it covers not the function, logic or algorithms and contains no intelligence for the home automation functions. What are the major advantages of MQTT for the Smarthome Control? The MQTT broker is fast, reliable and can easily be set up redundantly. MQTT is being used in the industry since many years and is there a well-proven technology. Very helpful is the fact that MQTT runs on many platforms so that we are not limited to a specific system. There are MQTT solutions for Windows, Linux, Raspberry Pi, Docker, but also for the Arduino world. For us, its installation is a piece of cake since MQTT needs no specific configuration or adaptation for a specific system. And even nicer is the fact that MQTT needs no modification or maintenance while our smart home system is continuously growing and changing. MQTT provides us a maximum of flexibility, extendability, modifiability and redundancy for the smart home infrastructure. It allows any number of independent brains within the infrastructure for signal evaluation, arbitration, algorithms, command execution or information distribution independently from their hardware and software platforms. It enables central and/or decentral function control. We can freely decide where to run any control logic. The rest of the system is not affected by that when using MQTT. Once our system gets more complex, or if we must go through troubleshooting, then MQTT is very helpful because we can add diagnostics or debugging functions at any time, separately and independently, without influencing the main control functions at all. This is of course only possible if the rules are followed that I show here later in the video. MQTT is for me the best tool to set up the home automation system in the very simple and clean way. We know the idea of KISS. Keep it simple, stupid. Everybody can do things in a complicated way, but simplicity is an art for which MQTT is very helpful. Let's come to the basic rules now. The MQTT broker controls the publish-subscribe mechanisms for the signal distribution. A client, for example a sensor, offers its information to the system by a publish to the MQTT broker. Another client, for instance the main control or an actuator, can subscribe to this particular information and gets it then automatically forwarded by the broker. The sensor must not know the main control or the actuator. It does not care who receives or uses this information. The main control must not know the sensor, it does not care where the information comes from. Topics like security and reliability will be discussed in an upcoming video. The main control must not know the actuator. The interpretation of a command is all up to the addressed hardware device. It is just important that it returns a feedback which allows the main control or other instances to know if the command was processed correctly. The main control can receive sensor values and can send commands without knowing the hardware or software environment of the information source or command's receiver. It must not even know the physical message submission channel, which normally could be a problem when gateways or bridges come into play. The actuator must not know the sensor or the main control. It does not care where the command comes from. The signals or commands or messages on MQTT are sent as payload within topics. A topic is, so to say, the name of the signal or command or interface. The payload is the content of the message, which can be a number, a value, a string, a text, JSON formatted content, and so on. The topics can be given almost any name and can be added freely at any time, even during the running system. There is no need to fix the system definition right at the beginning of the project in all detail. However, main signals and commands should follow standardized rules so that the communication can be structured in a common way for better clarity. A topic can be structured completely freely. There are only a few restrictions regarding special characters and MQTT internal special topics which are used for the maintenance of the MQTT broker. Here is a simple example for a smart home application. Topics for values from sensors could be named like this: home bathroom temperature for the output value of the temperature sensor in the bathroom, home kitchen temperature for the output value of the temperature sensor in the kitchen. For the submission of a sensor value, such a topic name is fully sufficient. The name of this topic already describes what payload content can be expected, which is here the temperature value, and where it comes from, which is here the room. A device can subscribe to a topic directly or by using a wildcard to a number of topics simultaneously at once. It can receive, for instance, all temperature values of the house with only one subscription. That could look like this. But it is a different story with the submission of command to an actuator. The target and the content of the message must be reflected in the name of the topic. The name of a topic for the submission of commands should tell that the payload contains a command. Topics for commands for actuator control like relays, motors, dimmers, and so on could be named like this: home, bathroom, command, heat valve for the command to the heater valve in the bathroom, like on, off, PWM value, and so on. Or home, kitchen, command, room lamp for the command to the room lamp in the kitchen, like on, off, dimmer value, color. Here is clear that this topic is a command topic, but you can name it as you like. Topics for feedbacks from actuators, for instance, their status, could be named like this: home, bathroom, stat, heat valve for the status of the heater valve in the bathroom, again like on, off, PWM value, or home, kitchen, stat, room lamp for the status of the room lamp in the kitchen, again like on, off, dimmer value, color, or maybe error. Here is clear that this topic is a status topic, but also here you are free to choose a name. The name or structure of a topic is an individual matter of taste. There is no universal solution. It should not be too complex or too long in order to minimize data traffic. It should follow a clear and simple structure. The freedom is almost infinite. There are industrial environments where up to 10 million topics are possible, by far enough for a private smart home system. Let's see now the correct process when consistently using MQTT. We got 4 independent clients in the same network connected with the MQTT broker. We have one sensor, one main control, and 2 actuators, which are one display and one valve. First of all, the clients must tell the broker what they want to subscribe to and send a subscribe request with the required topic names. The main control and the display subscribe to the bathroom temperature, and the valve subscribes to a command. The sensor sends a publish with the mentioned topic to the broker, which forwards it directly to the corresponding subscribers. The display shows the temperature value, and the main control then processes that value and decides what to do with it. It wants to raise the temperature and sends a command to the valve by a publish to the broker, which forwards it directly to the corresponding subscriber. The valve opens up as requested in the command. The sensor measures the temperature and publishes the new values to the broker without caring about what happens with that message. Now we see clearly that these clients do not know each other and have no direct connection at all. They communicate exclusively with the MQTT broker. So, what happens during the subscribing process? When receiving a subscribe request, the broker creates or appends to an internal table in which it saves the topics and the corresponding device IDs. This is an automatic process with any subscribing request coming from a device. From the previous example, we take two clients that subscribe to the bathroom temperature and one client that should be receiving a command. The broker now memorizes which client subscribes to which topic. Here we see this topic, the temperature, and the two device IDs that have subscribed to that one. And we see the command topic, which is supposed to go to client number 3. The subscriber table must and cannot be created manually, since this is an automatic process of MQTT. Only the client which has subscribed to a topic can unsubscribe to that topic. Once it is in that list, it cannot be easily removed or excluded. After the replacement of clients, their subscriptions typically still survive in that list unless they have correctly unsubscribed before they were taken out, which is unlikely if they just die. It means after a while there are potentially several dead entries which normally should not cause any problem, but we should know about it. After receiving a published message, the broker looks up in the table who has subscribed to that particular topic. It then forwards the message directly to the corresponding subscribers. The published topics can be of any type or name and can be even new, so that the broker does not know them yet. The broker forwards the messages only when it found an identical topic in the subscriptions list. It uses no additional decision rules or filtering. It cannot exclude specific subscribers from a particular topic. That is indeed technically possible with some brokers, but extremely complex and effortful for the definition and maintenance of the total system. That's why we ignore this function. If a client should not always receive a particular topic, we must create a separate and individual topic just for that and must organize the filtered distribution inside our Smarthome main control. What means QoS and retain? Along with the message, we can define a so-called QoS, quality of service, and set a so-called retain flag. I am not going to explain here all the technical details of QoS and retain. This has been perfectly explained in many other videos and blogs already. But I would like to demonstrate the main differences and their effect in practice. With QoS 0, the MQTT message will be sent once and nobody cares if the subscribers have received the message or if they are physically connected or if there were any technical submission problems. It's just a simple fire and forget. Client 1 publishes its sensor value to the broker, which forwards the message to all active, means connected clients. In this example, only client 2. Client 4 is currently disconnected and will not receive that message. Even after successfully reconnecting, it will still not receive that message and nobody notices that. The freshly reconnected client will receive a message only with the next publish that comes in. With QoS 1 or 2, the MQTT message will be temporarily stored and sent to the subscriber as soon as it is reconnected in case it was disconnected before. The broker memorizes in its table which subscriber has received the message and which one has not. Client 2 was connected, therefore received the message. Client 4 was disconnected and has not received it yet. If known clients reconnect, then the broker sends them all the stored messages without needing an external trigger. But be careful. In worst case, this can end up in an impressive firework of functions if many consecutive on-off commands were stored over time and then sent in one row. This can have potentially catastrophic effects, as you can imagine. This is all handled automatically by the MQTT broker and nobody else must take care about these tasks. However, It is only useful as far as the pure physical connection is concerned. The reason is MQTT cannot verify the content of the message or the command. The protocol monitors only the physical connection. Unfortunately, this leaves us without an essential part of control. MQTT can never tell if the receiver has properly done what we have expected it to do. Therefore, we must use an additional method which allows diagnostics or function monitoring for the control logic. For example, in case a feedback as part of an additional MQTT message is not returned by the receiver, the control logic can easily detect a connection problem or communication or processing misbehavior. With the setRetain flag, the MQTT message will be stored by the broker and forwarded to the subscriber as soon as it connects with the broker. The difference here is, even newly added subscribers will be receiving the message immediately upon subscription, even though they have not been present in the subscribers list before. The sensor publishes its value along with the retain flag setting. The broker stores that value and forwards it to the connected clients. If now a completely new or previously unsubscribed client sends a subscribe request, the broker will add this client to its subscriber table and forwards the stored value immediately to the new client. This allows, for instance, that the last published temperature value can be sent to any new subscriber without needing to wait for the sensor to publish an updated value. That is indeed quite nice and helpful, but for me it is not logical that the sensor is responsible to set the retain flag, since the sensor is not supposed to know what happens with its information and who is going to receive it for what reason. The risk is the following. If the sensor needs to be replaced, it is almost for sure that we will forget to set the retain flag in the configuration of the new sensor. The effect then is that our smart home will not work correctly anymore. That will surely make the entire planning and maintenance of our control logic unnecessarily complex, and troubleshooting will be like going through hell. It takes days to discover such an error. We remember, KISS, keep it simple, stupid. Such a structure is not simple. Values that are to be provided to any clients at any time must be stored centrally in the Smarthome main control as variables and sent to the clients in a controlled way. Does it make sense to use these functions QoS and retain for our Smarthome control? I personally never use QoS and retain at all. These surely powerful functions of MQTT are in fact very often the reason for big trouble. The well-known ghost switching is almost always caused by a chaotic usage of QoS and retain flags. Suddenly a device turns on or off and nobody can explain why this happens right now. In a complex smart home environment, you can easily lose the overview. Nobody starts with a completely predefined and fully perfect concept of a home automation control system. Typically, the smart home grows dynamically over time and changes quickly as the experience picks up with the use cases and functions. You quickly realize that not every potential situation was properly considered or anticipated, and then the control logic and the algorithms need to be modified. In that case, it is almost impossible to identify and modify any predefined QoS or retain flags afterwards, especially when those flags are set within self-written program code. In many cases, ghost switching can only be eliminated by deleting the entire MQTT subscription table file. To do so, the broker must be stopped, the table file must be deleted manually, and after that the broker must be restarted. If the Mosquito MQTT broker is being used, the process looks like this. The broker creates a fresh file automatically and all should be fine then. That is rather simple to do, but it should not be a regular task as it is easily forgotten and it is not an elegant solution anyway. Potentially, the problem can even occur again if the hidden root causes of a chaotic setup still persist. The MQTT broker can certainly be helpful with these functions or flags, but then the system is no longer under your own control. Personally, I don't like that idea at all. I prefer keeping control over my system by myself. Let's summarize now the basic setup for an MQTT network. The structure, content and number of topics is almost limitless and can be expanded even while the system is running. Changes in the structure of topics are always possible, but this must be reflected in the programming of each individual sensor, actuator, and in the control logic, which means extremely high effort to spend. The MQTT broker itself is completely not affected. It only processes the message forwarding. Firstly, define the topic structure thoroughly, perform a few try runs, then freeze the structure and keep it as long as possible. Special functions like QoS and retain flag are useful in specific cases, but they cannot provide a suitable function monitoring or diagnostics. These MQTT internal functions are often the reason for big problems within the running system. Troubleshooting is extremely complicated. A proper maintenance and control over QoS and retain flags is nearly impossible in big and complex environments. My recommendation: avoid the use of QoS and retain flags completely. Monitoring the presence or availability of devices can be done in many different ways. More important is a proper feedback or the diagnostics of command processing. Any receiver of commands must return its status so that the sender of the command can positively detect any failure of the process. MQTT internal functions can only monitor the physical connections. MQTT itself can never verify the expected reaction to a message or a command. Every command must be reflected from the receiver by using a feedback topic that is returned to the sender of the command as status feedback. How did I make my system redundant? In my professional life, I am almost paranoid when it comes to functional safety. I work on complex electronic architectures in the automotive industry, and there we have very strong requirements. In my system setup, I have established full redundancy in the following rather simple way. It not only covers the MQTT broker, but also the entire home automation control system, which is mainly running on Node-RED and a few Python scripts. The dashboard currently is created by using Node-RED also. I have no other application running, such as Home Assistant or I/O broker or whatever else. I use a second Raspberry Pi, which is a 100% clone, which herewith carries the identical host name as the first one. An ESP8266 monitors the condition of the main control unit by a hardware and software heartbeat. If something stops responding, then it triggers the bistable relay for the power supply. The main control unit will be cut off while the substituting control unit is being powered up. The rest of the network sees only a short interruption, but after booting is finished, the entire system continues nearly unaffected. Important: both Raspberries must never be active at the same time, as this would otherwise cause conflicts in the router. The MQTT broker is not being addressed by its IP address, but by the host name of the device it is running on. After reconnecting with the broker, all the clients or devices within the network must resubscribe to their topics and publish their current status in order to update the freshly started substitute control with the latest condition of the system. This must be considered in all the control programs. However, I can tell that the shown redundant control system has not been used ever since. My Raspberry Pi is running since 4 years, 24/7, fully reliably without any failure. Testing new functions or algorithms is being done on another Raspberry Pi. Using MQTT, I have full access to any signal, command or interface, even from that additional Raspberry, which makes testing new functions so easy without risking to messing up with the main control. That's why it might not be even necessary to create full redundancy to the entire home automation control system. Some sort of simplified emergency functionality on a third device might be fully sufficient, and a piece of cake by strictly using MQTT. This example shows clearly the power of MQTT and why I completely avoid the use of QoS 1, 2 or retain flags. All previously created publish-subscribe tables of the broker and all QoS or retain flags are completely gone after the switching. That's why from this point, any internal MQTT functions like retain are no longer available in the substituting system. After the switching, the substituting control runs a status request to all devices within the network. All devices must send their current status on MQTT. After that, all the function control logics and algorithms can resume their normal operation. However, there could have been active timers or counters which are not yet triggered in the substituting control. This problem can be solved for specific cases by creating a file in a central storage like a NAS drive, which logs all transient activities of critical functions. That saved content can be accessed by the substituting control so that the affected functions can properly recover and resume their work almost without any loss or uncomfortable interruption. The advantage of MQTT is that such functions for data collection and queries must never run within the main control program directly. Separate and independent programs can do that job by accessing the needed interfaces only through MQTT. After the system reboot, they do their job only once and will not be used until the next reboot. In an MQTT architecture, the main function control programs can be reduced to their core functionality. Any additional or auxiliary functions like logging, protocols, or status history and status recovery must not be part of the main function control. Such functions must be outsourced as independent subfunction modules like separate Node-RED flows or Python scripts, which can be implemented or modified at any time, even while the system is running. Any required status reports, commands, sensor values, variables or power states will be subscribed by such modules and saved to a central storage file like on a NAS. This data will be the base for various other applications such as the visualization of data history or statistics like nicely colorful diagrams, for instance, created by Grafana. It will also be useful for troubleshooting and analyzation of certain transients. Furthermore, it can be used for security applications like a presence simulation, which replaces recorded power states and sends out corresponding commands over MQTT. So we must strictly separate and outsource the auxiliary functions and connect the interfaces strictly by MQTT. As a result, the main control programs will be reduced to their very basic function logic without the hassle of handling hardware interfaces or any tasks that are not directly related to their core function. And don't forget, keep it simple, stupid. Rule number 1 is, in order to create an optimized architecture, we must strictly ensure the separation of input, logic, and output. This is called function decomposition. Before function decomposition, we usually see the following situation. The main control software also reads in the hardware input directly, here the switch, and controls the hardware output directly, here the LED. The main function control covers not only the main function logic, but also all sub-functions that are purely related to the hardware handling. That requires a huge effort for the programming and testing and becomes extremely complex in the end. The switch, for instance, is being monitored on pin number 1, which means that the main program must define if it is a high active, low active or analog switch, if a pull up or pull down must be activated, and so on. The same problem on the output side for the control of the LED. Also here, any single hardware detail like the pin number must be clearly defined. In the program, then we see at least the following. If input pin number 1 is active, then activate output pin number 2. This is still a very simple if this then that logic, but the software code becomes relatively long and complex since all individual hardware specifications must be considered. In addition to that, all of the external interfaces to other components or modules must be defined and handled from within the main function program, for instance interfaces for logging or visualization. That is why we need a strict separation of hardware and main control software. Furthermore, we want our main control software programs to be portable and compatible so that we can easily remove them onto other platforms. As you see in this particular example, due to the strong dependency between the hardware and the main program, there is no chance to move the program to another platform like another computer or operating system without needing to modify it. Therefore, we separate the hardware from the main logic, which results in much simpler single components which are connected by MQTT. After function decomposition, the hardware is now functionally strictly separated from the main control software, even if it is located within the same device like the Raspberry Pi. We start with the component module read switch state, where the switch is monitored by a simple mini program which sends the switch state as an MQTT topic to the broker. That is all what this program does, nothing more. It is a very simple if this then that logic. If input pin number 1 is active, then send on the topic switch 1 the payload on, respectively send and off. The publishing is done only once whenever the switch state changes. This mini program can now be reused many times by simply copy-paste it for any available input, but don't forget the pin number and topic name to be modified. There is no direct relationship to a main control function. Now we come to the real main Smarthome functional component. This one is supposed to turn on a specific lamp if the corresponding switch is activated. Except here we have no direct relation with the attached hardware. We exclusively use virtual signals, which are here the MQTT topics. On the output side, also here we only send another MQTT topic with a command. By the way, the command in the topic name is not mentioned here for space reasons, but it should be part of it. So the program for this function or logic looks as follows. Again, we have a very simple if this then that logic. If the topic switch 1 sends an on state, then send on the topic LED1 the payload on, respectively send an off. Also here, the publishing is done only once whenever the switch state changes. We conclude with the component module control LED. That mini program receives the command on the topic LED1 and carries it out by activating the output pin. Also here we have a very simple if this then that logic again. If the topic LED1 sends an on command, then activate the output pin number 2, respectively deactivate that output. This mini program again can now be reused many times by simply copy-paste it for any available output, but again don't forget the pin number and topic name to be modified. There is no direct relationship to a main control function either. As a result, we get a hardware-specific input module, a pure software-specific logic module for the main functions, and without any direct connection to hardware, and a hardware-specific output module. This was the necessary and important function decomposition. Now everyone can see how simple our Smarthome control can be built thanks to MQTT. After the separation of the function modules, they can be easily distributed over the entire network system. The logic modules will be moved into the central control unit. The hardware modules will be moved into the zone control units. These are the devices near the corresponding input-output zones. Any switches, sensors, actuators and displays will be connected here by using wires as short as possible. The only logical connection between all these modules is the MQTT broker. All these modules can certainly still be physically located within one common device like the Raspberry Pi, but even then they communicate exclusively over MQTT. The broker can also be located within that same device. A later separation and removal of any of the modules into another device is always easily possible. Here you see a short demonstration about how flexible we are now with the function distribution thanks to MQTT. The input module could be placed into zone unit number 1, the output module into zone unit 2. The logic module could be placed into the Raspberry Pi, the MQTT broker into a mini PC or a Docker environment. Any other combination is possible without influencing the interfaces between the main function and the hardware. The output module could just as well be inside zone unit 1. The main function does not see this difference. The broker could also sit inside the Raspberry Pi. The entire rest of the system sees no functional difference at all. If you wish to relocate the logic module into the mini PC, even at a later time, just go ahead, nobody sees a difference at all. Should one of the hardware units die, no problem, just replace the device and carry on, even if the zone unit now gets a totally different operating system or comes from a different manufacturer. We get a maximum of comfort and freedom with the design of our architecture. With all the nice arguments coming from the KNX lovers, the shown architecture is by far more flexible, compatible and cheaper than KNX can ever be. No ETS with software licenses is needed. No overpriced components are needed for building up a stable and future-safe system. The only potentially positive side of KNX is its communication bus, but the price influence of this bus is not reasonable to my opinion. If all hardware components on the market were able and allowed to communicate via MQTT, then we could easily have very flexible and future-safe smart home installations, and most of the currently existing incompatibilities and connection problems regarding adapters and ecosystem integration would just not exist. Forced cloud connections would be absolutely not necessary. We would no longer have to depend on fixed ecosystems that potentially stop their functions or services at any unexpected time. This brings us to the next problem, the bus technology. MQTT typically works only on TCP/IP with very few exceptions. When we use other types of physical connections like Zigbee, Z-Wave, KNX, CAN and so on, it will be a little more difficult. How should we integrate those into our home automation system? For that, we always need a gateway or bridge which connects the different physical standards. Not only that the protocols and the message structure are completely different, especially some of the wireless technologies are not always online in order to save energy, but if the interfaces of the gateways and bridges are strictly connected over MQTT to the rest of our Smarthome control, then we are almost as flexible as shown before. Future changes of the technologies are no longer a headache. With MQTT we are always on the safe side. Very important though, always and consistently, all interfaces must be passing through MQTT, never integrate them directly into the Home Automation main control program. Helpful programs like Home Assistant, IO Broker, FHEM, Node-RED and many nice tools more offer integrated adapters which allow direct communication with most of the mentioned physical connections or other ecosystems or tools. For example, Home Assistant offers an integration of Node-RED which seems very comfortable. I strongly recommend not to do that. We should always prefer the use of MQTT as a logical connection between Home Assistant and Node-RED. The reason is, this is not only comfortable, but also tricky as it leads to too much dependency on one particular ecosystem. With this, we easily lose the flexibility for later modifications, and portability of the main control program into another platform will be lost then. Besides a few Python scripts, I personally use mainly Node-RED for my home automation system. I simply love it, but all interfaces between the control logic and the hardware, and even between the function modules, run strictly through MQTT with no exception at all, even internally within my Node-RED flows. I use no direct links between the function modules. This gives me the flexibility to cut any function module out of Node-RED and create it within another platform without affecting the remaining function modules at all. MQTT keeps the modules always connected, no matter which environment they run in, which programming language is used, or over which kind of bus technology they communicate. For the shown example, should there be any functional dependency between the shutter control and the bathroom light, then it will be controlled by a separate function module using the MQTT interfaces. The zone units that I use are mainly based on ESP8266 or ESP32 processors. Important, all of these units are flashed with Tasmota. The only communication channel is MQTT. Especially for this usage, Tasmota is very useful. There are certainly other flashable solutions available, and they will be also just fine as long as they use MQTT. Only some of my zone units I have flashed with self-developed C++ code, as an exception only. The reason is, local pre-processing of time-critical data or Tasmota's built-in functionality is not sufficient for my particular application. Raspberries are also in use as zone units, mainly to work as local gateways. In there, I run only Python scripts. Whenever OneWire, Modbus or CAN are used as physical connections, then I integrate the corresponding gateways in those raspberries. In any case, the only logical connection is always the MQTT broker. Here we see now an example inside the Node-RED environment. We see a simple button, a switch and a text output for the dashboard of Node-RED. The switch and the button have the same function: turn the bathroom lamp on or off. The text output will only display the current state of the lamp. Why do I show this example? First, because here we can clearly see how strict I separate the function modules from each other, but how I connect them by MQTT. Second, because here we can potentially make two dangerous mistakes, which are made quite often but can be avoided very easily. In the settings of the button node, we must urgently ensure that the checkbox for the simulation of a click on incoming messages is not checked. Otherwise, we get a recursive loop which causes the system to crash. In the settings of the switch node, we must urgently ensure that the pass-through checkbox is not checked. Otherwise, also here we get a recursive loop which causes the system to crash. In order to see the real state of the function on the switch or button icon, we send the command from the switch or button to the actuators, but at the node inputs we connect the feedback, which is sent over MQTT coming from those actuators. We remember, each receiver of a command must return its new status as a feedback topic. Only then we can see on the dashboard the true state, which tells us if the command was properly executed. Another side effect is, if all the elements on the dashboard which are supposed to show a particular function state have subscribed to the same feedback topic, they will all show the same state. No further synchronization needed. That is exactly what we want. In the button node, I read the current switch state from the global variable and send then the opposite command to the lamp. In the switch node, it is not necessary to read the global variable because the switch node can already define the on or off command by itself. What else do we see on this example? For me, it is important that I can now take any of these elements out, remove them, delete them, modify them without affecting any of the other elements. Here I can use an additional function module which will set the global variables depending on the messages that come in on the feedback topic. By doing so, other function modules can always read those variables without needing to subscribe to the feedback topic also. Actually, case by case, we can decide which method is the most suitable one for our control logic. Here I define those global variables once when Node-RED is being started and initializing. By this I can define default values for particular functions or variables. Here I can turn the bathroom lamp on or off directly from inside the Node-RED development environment, without needing to access the dashboard. There is no influence on the main function logic at all. All communication uses MQTT. The bathroom lamp is connected by MQTT and does not care where the commands come from. It just does not see any direct connection to our control software. Let's see how much flexibility MQTT gives us for the architecture of our smart home system setup. In order to simplify our life, we can choose our most preferred tool and device for each individual task or purpose and connect all of them by MQTT. Each tool has its pros and cons, and not every tool is the perfect choice for all our needs and requirements. There is no black and white, and it is in fact not necessary to make a fixed choice on a particular solution. After time, we might even figure out that another tool or ecosystem might have been the better choice for us. The shown combination is just one possible scenario out of hundreds of possible scenarios that you can create. If you consistently use MQTT for the interfaces, then you are free to change your setup at any time without needing to modify the entire system. If you wish to change something, then you can even do it gradually and don't need to modify everything at once. I hope I have given you the answers to the given questions. Now it is up to you to become creative and optimize your smart home system with the same fun and energy that I have by working on my system.